Right now, Earth is hurtling through space at 67,000 miles per hour. You're on a rock, screaming around a ball of nuclear fire at speeds that would vaporize any human-made vehicle. And yet, you don't feel a thing. You're not being flung into the void. You're not spiraling into the sun. For over 4.5 billion years, Earth has traced the same path over and over with a precision that would make a Swiss watchmaker weep. What invisible force keeps our planet locked in this cosmic dance? The answer isn't what most people think. You've probably heard that gravity holds planets in orbit. That's true, but it's only half the story. Gravity alone would pull Earth straight into the sun in about 64 days. Something else is happening, something far more elegant than a simple tug-of-war between massive objects. Understanding what actually keeps planets in their orbits requires us to abandon almost every intuition we have about motion, stability, and what it means for something to stay in place. Let's start with what you think you know about orbits. Most people imagine planets sitting in space, held at a fixed distance from the sun by some kind of cosmic tether. The sun pulls, the planet resists, and equilibrium is achieved. It's a comforting image. It's also completely wrong. A planet in orbit isn't resisting anything. It's falling. Right now, Earth is falling toward the sun, and it has been falling continuously since the solar system formed. Every second of every day, gravity pulls our planet toward that massive fusion reactor at the center of our solar system. The force is relentless, constant, and it never stops. So why aren't we getting closer? Because Earth isn't just falling toward the sun. It's also moving sideways, perpendicular to that gravitational pull, at exactly the right speed to keep missing. Picture throwing a ball horizontally. It curves downward and hits the ground. Now throw it faster. It travels farther before landing, faster still, and it goes even farther. At some specific velocity, if you could throw it fast enough and there were no air resistance or obstacles, the ball would curve toward the ground at the same rate the ground curves away beneath it due to Earth's spherical shape. The ball would never land. It would be in orbit. That's what Earth is doing around the sun. We're not hovering in place, held by some invisible string. We're perpetually falling. But we're moving sideways so fast that we keep missing the thing we're falling toward. This is the secret to every orbit in the universe. Planets, moons, satellites, space stations, all of them are falling. They're just falling sideways. The speed required for this cosmic juggling act is shockingly precise. Earth travels at approximately 30 kilometers per second in its orbit. Not 29, not 31. If we were moving just 10% slower, our orbit would decay and we'd spiral inward. 10% faster and we'd escape the sun's gravitational grip entirely, shooting off into interstellar space. The margin for error is razor thin, and yet here we are, maintaining that exact velocity year after year, century after century, eon after eon. But where did that velocity come from in the first place? The answer takes us back 4.5 billion years to a swirling disk of gas and dust collapsing under its own gravity. As this primordial cloud contracted, it began to spin faster like a figure skater pulling in their arms. Within this rotating disk, clumps of material started colliding and sticking together, gradually building up into larger and larger bodies. Each collision added mass, but it also added angular momentum, that sideways motion we've been talking about. By the time a planet-sized body had formed, it had inherited the rotational motion of the entire disk from which it was born. That ancient spin became the orbital velocity we observe today. Earth isn't moving at 30 kilometers per second because something is pushing it. It's moving at that speed because that's the motion it was born with. And in the vacuum of space, with nothing to slow it down, that motion persists indefinitely. This is where Isaac Newton's first law enters the picture. An object in motion stays in motion unless acted upon by an external force. In the near-perfect vacuum of space, there's no air resistance, no friction, nothing to slow a planet down. Once Earth acquired its orbital velocity during formation, it simply kept going. The sideways motion that prevents us from falling into the sun isn't maintained by any ongoing force. It's maintained by the absence of forces trying to stop it. Gravity isn't fighting Earth's motion. Gravity is redirecting it, constantly bending our straight-line trajectory into a curve. Without gravity, Earth would fly off in a straight line, departing the solar system forever. Without that sideways velocity, gravity would pull us straight in. Together, these two factors create something neither could produce alone: a stable, repeating path through space. But I've been lying to you about something. I said Earth's orbit is perfect, that we trace the same path year after year with unwavering precision. That's not quite true. Earth's orbit isn't a circle. It's not even close to a circle. And that's where things get interesting. Part 2. What keeps planets in perfect orbits? In 1609, a German mathematician named Johannes Kepler made a discovery that shattered 2,000 years of astronomical belief. Planets don't move in circles. They move in ellipses. And that single observation changed everything we thought we knew about the cosmos. An ellipse looks like a squashed circle, an oval with two special points inside called foci. Here's what makes it different from a circle. In a circle, every point on the edge is the same distance from the center. In an ellipse, the sum of the distances from any point on the edge to both foci remains constant. Draw a line from one focus to any point on the ellipse, then draw another line from that same point to the other focus. Add those two lengths together. Now pick a different point on the ellipse and do the same thing. The sum will be identical every time without exception. The sun sits at one of these foci, not at the center where you'd expect it, at one focus off to the side. The other focus is just empty space, a mathematical point with nothing in it. This means Earth is sometimes closer to the sun and sometimes farther away. When we're at our closest point, called perihelion, we're about 147 million kilometers from the sun. When we're at our farthest point, aphelion, we're about 152 million kilometers away. That's a difference of 5 million kilometers, roughly 13 times the distance from Earth to the moon. You might think this would cause dramatic seasonal changes. It doesn't. Earth's seasons have almost nothing to do with our distance from the sun. They're caused by the tilt of our axis, but that's a different story entirely. What matters here is that this changing distance creates something unexpected. Earth doesn't move at constant speed around the sun. When we're closer to the sun at perihelion, we move faster. When we're farther away at aphelion, we slow down. This is Kepler's second law, the law of equal areas. Imagine drawing a line from Earth to the sun. As Earth orbits, that line sweeps out a wedge-shaped area like a slice of pie. Kepler discovered that this line sweeps out equal areas in equal times. If you measure the area swept in 1 week during January, it will be exactly the same as the area swept in 1 week during July. But since Earth is closer to the sun in January, the line is shorter, which means Earth has to cover more distance along its orbit to sweep out the same area. More distance in the same time equals higher speed. The numbers are precise. At perihelion, Earth travels at about 30.3 kilometers per second. At aphelion, we're down to about 29.3 kilometers per second. A difference of 1 kilometer per second might not sound like much, but at these speeds, it represents a 3% variation. We're constantly speeding up and slowing down, accelerating and decelerating, not because anything is pushing us, but because gravity's strength changes with distance. Here's where it gets beautiful. The closer you are to the sun, the stronger its gravitational pull. That stronger pull accelerates Earth, making us move faster. As we swing around and start moving away, gravity starts working against our motion, slowing us down. It's exactly like throwing a ball straight up into the air. The ball slows down as it rises, stops at the peak, then speeds up as it falls back down. Earth is doing the same thing, except we're not going straight up and down. We're moving in an ellipse, perpetually climbing away from the sun, then falling back toward it, then climbing away again. Every planet in the solar system follows an elliptical orbit. Some ellipses are nearly circular, like Earth's. Our orbital eccentricity, the measure of how stretched out an ellipse is, sits at about 0.017. 0 would be a perfect circle. 1 would be infinitely stretched. We're very close to circular, which is why ancient astronomers thought our orbit was a circle for so long. The deviation is subtle. Mercury's orbit is far more eccentric, about 0.206. Its distance from the sun varies by roughly 40% between perihelion and aphelion. Mars sits at 0.093, giving it noticeably more variation than Earth. Venus, on the other hand, has an eccentricity of just 0.007, making its orbit the most circular of any planet in the solar system. It's almost perfectly round, so close to a circle that you'd need extremely precise measurements to detect the difference. These elliptical paths aren't random. They emerge from the same swirling disk of gas and dust that form the planets. As material clumped together, gravitational interactions between protoplanets nudged their orbits into ellipses. Some interactions made orbits more circular, others made them more eccentric. What we see today is the result of 4.5 billion years of gravitational sculpting, a frozen record of countless interactions that occurred when the solar system was young and chaotic. But here's something that might trouble you. If planets are constantly speeding up and slowing down, if they're moving closer and farther from the sun, if their paths are ellipses instead of circles, how can we say these orbits are stable? How do we know Earth won't gradually spiral inward or drift outward over millions of years? The answer isn't as simple as you might hope, because in a solar system with multiple planets, all pulling on each other gravitationally, perfect stability becomes impossible to guarantee. And that's where the story gets genuinely unsettling. The solar system isn't a collection of isolated orbits, it's a network. Every planet pulls on every other planet. The sun dominates, yes, but Jupiter tugs on Saturn. Saturn tugs on Uranus. Earth and Venus influence each other. Mars gets jostled by Jupiter's gravity. These interactions are small, but they accumulate. Over millions of years, tiny gravitational nudges can add up to significant changes in orbital paths. This is called the N-body problem, and it's one of the most notorious challenges in physics. Two bodies orbiting each other, that's solved. We have exact equations describing their motion, but add a third body and everything changes. The math becomes impossibly complex. No general solution exists. You can't write down a formula that predicts where three mutually gravitating objects will be at any future time. You have to simulate it. You run the numbers forward step by step, calculating gravitational forces at each moment, updating positions and velocities, moving to the next moment. And when you add 8 planets, dozens of moons, thousands of asteroids, the problem becomes staggering. So how stable are planetary orbits? The answer depends on timescale. Over human lifetimes, perfectly stable. Over thousands of years, still stable. Over millions of years, mostly stable with tiny variations. But over hundreds of millions or billions of years, things get murky. Computer simulations reveal something unsettling. The solar system is chaotic. Not chaotic in the everyday sense, chaotic in the mathematical sense. Small changes in initial conditions can lead to wildly different outcomes over long time scales. If you could rewind the solar system 4 billion years and shift Earth's position by a single millimeter, by today, Earth might be in a completely different orbit, or it might not exist at all. The mathematics governing planetary motion is deterministic, meaning the laws are fixed and unchanging, but the long-term behavior is unpredictable. This is the essence of chaos theory. Order and disorder coexisting in the same system. Mercury is particularly vulnerable. Its orbit is more eccentric than Earth's, and it sits close enough to the Sun that relativistic effects become important. General relativity predicts that Mercury's orbit precesses, meaning the ellipse itself slowly rotates over time. Newton's laws predict precession too, but not quite enough. Einstein's equations match observations perfectly. This precession interacts with gravitational tugs from other planets in complex ways. Simulations show that over billions of years, there's a small but real probability that Mercury's orbit could become unstable. It might crash into Venus. It might get ejected from the solar system entirely. The odds are low, roughly 1% over the next 5 billion years, but they're not zero. Jupiter plays a critical role in the solar system's stability. Its mass dwarfs everything else. 318 Earths could fit inside Jupiter's mass, more than twice the mass of all other planets combined. When Jupiter moves, the entire solar system feels it. Jupiter's gravity clears regions of space, sweeping up asteroids and comets that might otherwise collide with inner planets. The asteroid belt between Mars and Jupiter exists because Jupiter prevented those rocks from coalescing into a planet. Its gravitational influence kept the region turbulent, causing collisions instead of accretion. Jupiter also acts as a shield. Comets from the outer solar system that swing inward often encounter Jupiter first. Some get captured, some get flung outward. Some collide with Jupiter directly. In 1994, astronomers watched comet Shoemaker-Levy 9 break apart under Jupiter's tidal forces and slam into the planet in a series of spectacular impacts. Each collision released energy equivalent to millions of nuclear bombs. Dark scars marked Jupiter's atmosphere for months. Without Jupiter, Earth would experience far more impacts from comets and asteroids. Life might never have gained a foothold, but Jupiter's influence isn't purely protective. Its gravity also perturbs the orbits of smaller bodies, sometimes sending them careening into the inner solar system. The relationship is complex. Jupiter stabilizes some orbits and destabilizes others. It depends on distance, on orbital resonance, on the specific configuration of bodies involved. Orbital resonance deserves special attention. This occurs when two orbiting bodies have periods that form a simple ratio, 3:2, 4:1, 2:1. When resonances occur, gravitational interactions happen at regular intervals, reinforcing each other. Some resonances are stabilizing. Pluto and Neptune are in a 3:2 resonance. For every 3 orbits Neptune completes, Pluto completes 2. This locks their orbits in a configuration where they never get too close, despite Pluto's orbit crossing Neptune's path. The resonance protects Pluto from close encounters. Other resonances are destabilizing. They amplify perturbations instead of dampening them. Objects in unstable resonances with Jupiter get ejected. The asteroid belt has gaps called Kirkwood gaps, where almost no asteroids exist because those orbits are in unstable resonance with Jupiter. Any asteroid that wanders into a gap gets gravitationally kicked into a different orbit relatively quickly, on astronomical timescales, millions of years instead of billions. The long-term fate of planetary orbits remains uncertain because chaos makes precise prediction impossible beyond certain timescales. We can say with confidence that the major planets will remain in roughly their current orbits for the next few 100 million years. Beyond that, uncertainty grows. Statistical studies suggest the solar system is broadly stable for billions of years, but extreme outcomes, while unlikely, cannot be ruled out. Mercury might destabilize. Mars could be ejected. Earth's orbit could shift enough to dramatically alter climate over geological timescales. This uncertainty isn't a failure of science. It's a fundamental property of the system. The laws governing orbital motion are perfectly known. We understand gravity with exquisite precision, but knowing the laws doesn't guarantee predictability when the system is chaotic. The solar system has been stable for 4.5 billion years. That's strong evidence for continued stability. But evidence isn't proof. The mathematics allows for scenarios where stability breaks down, and that brings us to something even more fundamental about how orbits actually work. Because a planet isn't just falling toward the sun, it's falling around the sun. That distinction matters more than almost anything else in understanding orbits. Imagine firing a cannonball horizontally from a mountaintop. It arcs downward and hits the ground some distance away. Fire it faster and it travels farther before landing. Fire it fast enough and something extraordinary happens. The cannonball falls toward Earth, but Earth's surface curves away beneath it at exactly the same rate. The cannonball never hits the ground. It keeps falling forever, circling the planet. That's an orbit. Perpetual falling that never reaches the surface because forward motion carries the object around the curve faster than gravity pulls it down. This applies to every orbiting body in the solar system. Earth falls toward the sun continuously but moves sideways fast enough that it misses. The moon falls toward Earth but moves sideways fast enough to miss. The International Space Station falls toward Earth but moves sideways so quickly it traces a circle. Astronauts inside aren't floating because gravity disappeared. They're floating because they and the station are falling together at exactly the same rate. Everything inside experiences weightlessness, the sensation of continuous free fall. Newton understood this perfectly. He imagined a cannon on a mountain firing projectiles at increasing velocities. Slow shots hit nearby. Faster shots travel farther. Eventually, one shot reaches orbital velocity and circles the planet. Fire it even faster and it spirals outward into an ellipse. Fire it faster still and it escapes entirely, breaking free from Earth's gravitational influence. The principle scales to any gravitational system. Planets, moons, artificial satellites all follow the same rules. The exact velocity required depends on 2 factors: the mass creating the gravitational field and the distance from that mass. Closer orbits require higher speeds. Mercury screams around the Sun at 47 kilometers per second. Neptune crawls at 5.4. Mercury needs that speed because the Sun's gravitational pull is vastly stronger at Mercury's distance. Neptune moves slower because gravity weakens with distance. The relationship follows an inverse square law. Double the distance and gravity becomes 1/4 as strong. Triple the distance and it becomes 1/9 as strong. This creates something profound. Every stable orbit represents a perfect balance. Gravity pulls inward with exactly the right strength to bend the planet's straight-line motion into a curve. Change the planet's speed even slightly and the orbit shifts. Speed up and the orbit expands into a larger ellipse. Slow down and it contracts. Change the speed at just the right moment, and the orbit becomes more circular or more elongated. Spacecraft use this constantly. Firing engines at specific points in an orbit allows precise control over the trajectory. Raise the orbit on one side, lower it on the other. Shift from circular to elliptical or back again. But what creates that initial sideways motion? Why do planets already have the velocity needed to orbit instead of falling straight into the Sun? The answer reaches back 4.5 billion years to the formation of the solar system itself. The solar system formed from a rotating cloud of gas and dust. Everything in that cloud carried angular momentum, the rotational equivalent of linear momentum. Angular momentum is conserved. It cannot be created or destroyed, only transferred. As the cloud collapsed under its own gravity, conservation of angular momentum forced it to spin faster. The same principle makes figure skaters spin faster when they pull their arms inward. The collapsing cloud flattened into a disk because rotation prevented collapse along the plane of rotation, while gravity continued pulling material inward perpendicular to that plane. The Sun formed at the center where most of the mass concentrated. The planets formed farther out where material coalesced into larger and larger bodies through collisions and gravitational attraction. Everything in that disk was already moving sideways, already rotating around the center. The planets inherited that motion. They didn't need to be launched into orbit. They were born moving, circling the forming Sun as part of the disk's overall rotation. That inherited motion persists. There's no friction in space to slow the planets down, no air resistance, no drag. Once in motion, an object continues moving at constant velocity unless acted upon by an outside force. That's Newton's first law. Gravity provides the outside force, but gravity acts perpendicular to the planet's motion, bending the path into a curve rather than slowing it down. The planet's forward speed remains essentially constant. What changes is the direction. This explains why all the planets orbit in roughly the same plane and in the same direction. They all formed from the same rotating disk. The disk's rotation determined the direction. The disk's flatness determined the plane. Even today, billions of years later, that original configuration persists. The planets haven't scattered randomly through three-dimensional space because they started with aligned angular momentum, and nothing has disrupted that alignment enough to change it fundamentally. Disruptions do occur on smaller scales. Asteroid impacts can tilt a planet's rotation axis. Gravitational interactions between planets cause small perturbations. Tidal forces slowly transfer angular momentum between bodies. But the overall architecture remains stable. The disk's ghost still shapes the solar system. Understanding this transforms how you see the night sky. Every planet, every moon, every asteroid is exactly where it is because of a balance between motion inherited from the solar system's formation and gravitational forces bending that motion into curves. Change either component and everything shifts. Increase a planet's speed and it drifts outward. Decrease its speed and it spirals inward. Alter the Sun's mass and every orbit adjusts simultaneously. The system is dynamic, constantly responding to forces, constantly maintaining equilibrium through motion. That equilibrium isn't accidental. It's the inevitable consequence of gravity acting on objects that already possess velocity. The planets aren't locked in place by invisible chains. They're trapped in patterns of perpetual falling, missing the Sun over and over, tracing the same paths because the mathematics of gravity and motion allows nothing else. The orbits are perfect, not because someone designed them, but because imperfect orbits don't last. Bodies on unstable trajectories either collide with something or get ejected. What remains after billions of years are the configurations that work, the patterns that persist, the balance between falling and missing that defines every orbit in the cosmos. The universe isn't holding planets in place, it's letting them fall forever in precisely the right direction. That's the answer hiding in plain sight. Gravity doesn't anchor planets like chains holding a ship. It curves their motion like a river bending around a stone. The planets aren't fighting to stay in orbit. They're following the only path available to them given their speed and the sun's gravitational pull. This is what makes orbital mechanics so elegant. There's no struggle, no force opposing another force, no cosmic tug of war, just objects moving through space, following the curves that massive bodies create in the fabric of space-time itself. Earth will continue this dance for billions of years, falling toward the sun at 67,000 miles per hour, missing it with every passing second, tracing an ellipse carved into the geometry of space by nothing more than mass, velocity, and the unchanging laws that govern them both. That's the machinery underneath the sky. That's what keeps planets in their orbits. Not magic, not design, just physics playing out the only way it can. And somehow, that makes it more remarkable than any other explanation ever could.